So, good evening. Today's talk is one on quantum entanglement. This is one that I did for the Research Triangle Quantum Computing Meetup group recently. So, I've always been fascinated by several aspects of quantum mechanics, and of course, measurement is a big one, determinism. Entanglement, though, is the most mathematically interesting, in my opinion, because it's the one where there really isn't a mystery as to what it is, but somehow in the course of many repeated quantum courses, people still end up not exactly knowing what they're talking about. And I'm not going to pretend like I'm different than that. I spent many, many years trying to make sense of this, and the books weren't really as helpful as I think they should have been. If you are a very algebraically minded person, you may come to a place where you're satisfied. But if you're a geometrically minded person, you'll probably be pretty frustrated. So let me begin. So the first thing you might notice is I've put up this initial slide, almost a teaser, where I use the phrase basis representation versus continuous geometry. It's not very illuminating, but I mean it to suggest something later on, because I'm going to be giving a very geometric picture of entanglement. And one of the reasons people find entanglement so difficult is, one, usually the examples involve spin, which is one of the least classically commensurate ideas of quantum mechanics. So hard to get your mind and intuition around it. The other is that when you learn quantum mechanics, you usually learn about the Heisenberg interpretation, and the Schrodinger interpretation, or pictures, I should really say, Heisenberg pictures. And the Heisenberg was very much matrix mechanics, very consistent with when we think of basis representations, with our bras and our kets and our basis sets. But it was Schrodinger, when he came up with wave mechanics, that we really had a very nice geometric picture, and this fueled an awful lot of progress. They might technically be equivalent pictures, but the Schrodinger picture really just works for us in a better way, and it led to a lot of solutions that were pretty hard to come by based on the Heisenberg picture. So when I think about entanglement, the usual way people approach this is through basis representations. You will have your entangled spins, and you will come up with something, and you will project it through your interferometer, and you will measure these things and get your Bell statistics or something like that, in which you will argue, well, there's no hidden variables, or this entangled thing is real. However, I'm going to put forward a continuous picture in terms of geometry. So I'm not going to use spin at all. And I'm going to bring up some important points about what many-body quantum mechanics has to be. And when I say that, I'm really getting an idea that I and many other people have, that really the wave functions are the reality, and that whatever measurement is somehow buried in this description. So many people use the word many worlds, and I believe of that in a definite way, but a very precise way, which maybe in a later talk I'll bring up. A lot of the problems with quantum mechanics, in my opinion, is it's either very formal, or we get away with a lot of kind of hand-wavy explanations to justify the calculations that work. And if you've been doing quantum mechanics for a long time, you might have realized at some point that there's an awful lot of calculations out there that didn't work out at all, but seemed conceptually just as well justified as a lot of the ones that worked. So clearly quantum mechanics has in it an awful lot of the reality we have, but it would be nicer to have something cleaner that gets us from our concepts to our calculations, instead of feeling like I've just had to learn a whole bunch of kinds of calculations that worked out and mimic those in places, and then there are problems where we don't really know how to proceed. Feels like if this was more clean and deterministic, maybe we wouldn't have these problems. But that's a slightly different topic. So let's go on to the next slide. So for starters, I'm going to cover just a few points of quantum mechanics leading into where we're going. There is this picture we have of wave functions based on various forms of imaging. Some are very sophisticated, some are like the scanning tunneling microscopes. But we have this idea of solids as these, sort of balls of atoms. You get an idea from the hydrogen atom that maybe these are like the electron clouds, and they sort of taper off slowly. And then we have this idea of indistinguishability of these. So maybe all the green ones are the same. One thing that always bugged me is if these are indistinguishable, I look at those atoms and I see that, well, that one's there and that one's there, so haven't I distinguished them? It's kind of like that young Frankenstein when he says, like, where? Werewolf. There. There, wolf. So the indistinguishability notion is somewhat annoying. It really is about symmetry. These are high-dimensional wave functions that have symmetries over their coordinates. And we'll get more into that later, but the indistinguishability thing can lead you a little astray. But these look believable. Like these are actual some images. Like there's an electrons wiggling around, obeying wave functions. So it's a pretty compelling picture. But it does make you wonder, like, what is different between quantum mechanics and classical field theory? Because classical field theory describes electromagnetism, gravity, all sorts of classical fields. And when we set up quantum mechanics, well, we write down things that are classical fields, like the Schrodinger equation it's like a classical field. And until you get to the point of measurement, it certainly behaves like a classical field. So the things that really distinguish it are two things. One, what happens at measurement. And the second thing has to do with what I would describe as high dimensionality. For example, if I make a hydrogen atom, we tend to think of that as like, oh, it's a little ball with an electron cloud around it. Really it is a 6-dimensional wave function and not 2 3-dimensional wave functions or a 3-dimensional wave function around an atom. And as you add particles, that picture is inescapable. So if you believe that quantum mechanics can be described in some way by classical field theory, it has to be a high-dimensional one. And this is ultimately where the questions of entanglement come about. So let's talk a few things about measurement, since they're pretty central to what quantum mechanics is. There's this business of the collapse of the wave function, where it goes from, at least people used to think, it goes from this wave-like property to this point-like property. Back when people were really believing complementarity was at the core of quantum mechanics, it was very important to think that, oh, there's a classical piece of the world and a quantum piece of the world. The quantum stuff was really small stuff. Now we know this is kind of not really very good, because we certainly have very large quantum mechanical effects we observe in delocalization on very large scales, superfluidity, superconductivity. These are large scale effects. So the scale thing doesn't really cut it. We also believe that there are special observables that correspond to measurements. I don't know which ones those are. It would be really nice if quantum mechanics could tell us what we were going to measure based on how we arranged some wave functions to make a device. There's the formalists, people like Dirac and von Neumann, and if you look at Cohen-Tanuji's book, the linear self-adjoint operators that correspond to measurement devices. It was the same question of how do I know which devices correspond to which measurements. I mean, you really still need this question of a division between classical and quantum worlds to make that distinction. Hidden variables, Bohm, and people like that tried to find ways around this to describe the particles as point-like, but described by some governing wave. And then there are people who mess with the idea of what logic means itself, like Bayesian methods and fractional logic values, things like that. One of my graduate classmates, Chris Fuchs, is known for this approach. I don't buy it at all, so I'm not going to talk about it. Okay, so how about the two most intuitive variables, maybe position and spin. These are what we're always talking about. Like we can talk about momentum, space, and other things like that, but position feels like the world we live in. Things are described with respect to position. And spin effects, which are very counterintuitive. So, but again, it feels, this still feels very much like classical field theory. We have partial differential equations, and then they give deterministic evolution. If you're talking about spins, then, well, you have ordinary differential equations over discrete values. Discrete values in the sense that there's discrete levels of the spin, unlike continuous locations for the wave function. These are very handy for quantum computing, and most discussions on entanglement involve spin. So there are some paradoxes and troubles here. There's the lack of determinism, tend not to like it, probabilistic results go along with that. It's not just probability either. I mean, there are people who approach classical mechanics probabilistically, but it seems like there's something below the probability, these complex amplitudes that then we churn into probability. So even less intuitive. There's a little magic of measurement relating to our devices and why they do what they do. And then, of course, there's the entanglement thing, which we're going to talk about more about, which usually makes people feel like there should be something faster than light going on. So, all right, so I'm going to discuss a very basic example here. And it's to kind of make a mapping between two particle space in classical physics and that in quantum mechanics. No spin. Everybody, in fact, everybody lives in line land, not even flat land. We live in a one-dimensional world. I've got two ants. I didn't have a good satisfying ant icon, so I used a happy face and a flower. So let's just say we live in line land, and happy ant is at 1 meter from me, and flower ant is at 3 meters from me. So there's an equivalent way I can view this, and that is instead of viewing them as 2 points on a line, I can view them as 1 point in a plane, and I can map the equations of motion or whatever, or their evolution. Instead of two particles moving around, I can take this 1 point in the plane and move it around. It's not especially interesting at the moment, but the first thing to point out is the correlation of position is everything's perfectly correlated. Basically, if the first ant is at location 1 and the second ant is location 3, the probability of that is 1. Every other possibility, the probability is 0. Again, not really interesting yet. So now, let's say instead of these being ants, let's say there were little wave functions, like little wave packets, sort of located, centered about those positions 1 or 3. Well, now I can think of them, okay, I can just see them as two little wave packets that sort of live and spread out on this line. But I can also play the same game of how would this look in a two-dimensional space with a single wave function. All right, so I can do that. And the way I do that, for various reasons, is I multiply them together. So you can see I've got x1 in one direction, x2 in another direction, and so if each one of these had like a little finite support to it before they went to 0, when I multiply them together, I end up with a wave function that now has a rectangular support. And it's more than that. I mean, the property of being a product function is very specific. So I could have non-product functions that had support of a rectangle. But, and then I could do the same thing. I could evolve these wave functions in each separate direction as though nothing special was going on. So as I said, the support of the functions is a rectangle. If we were talking about differential equations, we would become these separable. We'd be like we had a separable differential equation. We would be looking for functions that were products of functions over lower dimensional spaces. That doesn't mean that the general solution is one of those, but it could be made as a linear combination of them. Again, the probabilities are independent in the traditional sense that I just multiply them together. Okay, so now things get a little weird because so far this picture has been isomorphic. I can think of this as line land or plane land. But the thing that can happen is not all functions are product functions. So I couldn't take a general function on that 2D space and break it up and think of it as one function moving one way and one another. And you might say, well, does that ever really happen? And I'm going to show you examples that it does happen, and we see it all the time. And that means that our picture of line land with two particles or two ants or two wave functions in it is inadequate, that you really have to graduate to thinking of this as a two-dimensional space. Now you might say, well, but we live in 3 dimensions. Those ants live in 1 dimension. What are you talking about? Maybe this is just a mathematical intermediary thing we have to go through. But I argue that if the reality is this, then the space you live in has to be that. Maybe the mystery is not so much entanglement, but the mystery is how the heck do you take some high dimensional wave function and express a reality that seems so much like 3 dimensions to us or 1 dimension for these ants or whoever is measuring them. Anyway, that's mine. Opinion. Okay, so here's just a little picture of sort of a general function. I drew a general function with clearly a non-rectangular support and no other details. And so the moral of all this is, these ants' realities, so I argue that their world, their universe, really has to be at least 2-dimensional. And in 3 dimensions, what do you mean? Well, as I mentioned, the hydrogen atom is truly a 6-dimensional wave function. We can break it up into a 3-dimensional wave function of the relative coordinates, which we tend to think of as the electron, but really it's a combination of the electron-proton, and because the mass difference is really large, we get away with calling it the electron. And then a center of mass motion, which mostly involves the proton coordinate. And we can make a basis set of products of these. But of course, the general reality will not be that. It will be some combination of them. Okay, and here's where we get to this thing I rip on chemists for a minute. I mean, I love chemistry. Chemistry is what got me interested in quantum mechanics in the first place. So I saw those orbitals and I thought, that's amazing. I really have to understand those, and dominated and wrecked the rest of my life. So we have this picture that we've been taught about all these orbitals, and get an idea of like, okay, well, those orbitals overlap and then they start forming new kinds of bonds like sp2 and sp3, hybrid bonds. In intro chemistry, you just kind of get shown the pictures. But later on, you might learn a little bit about molecular orbital theory and actually be able to calculate some of these things. And a lot of these models can work pretty well a lot of the time, but we hide stuff like we always do with electronic calculations, like the shielding of the internal orbitals. We get away with in chemistry and in solid state physics viewing things as calling things electrons and orbitals when we hide a lot of stuff with these nonlinear terms. The most honest people are probably the Monte Carlo, diffusion Monte Carlo people. They seem really clear about the complexity of the many-body wave function, and of course they're not visualizable. They're just way too big and complex. And they're also very well aware that even trying to plot these things on a grid, just like for 10 particles, pretty soon, if 1,000 data points per coordinate, 1,000 to the 10th, pretty soon you've got way too much data. You can't possibly even store it, much less do any calculation with it. So this is my spiel I mentioned before, is that if you have a high-dimensional wave function, why do we perceive our world as 3D? And I dedicated a chunk of my thesis to this, which no one read. That's fine. I pushed it here and there, but if you're interested, I'm going to make another video on it soon. You don't even have to go look it up. And I pretty much said all of that. All right, so most of the time when we're talking about things like this, you'll find we're talking about Bras and Ketz and Hilbert space. So we're talking about when the probabilities of being at first particle being at one point, second particle being at another point, is not equal to the probability of them being at each one separately. That's one way of saying that something's entangled. So I'm going to do a little example. I love lattice surgery, if you know what that is. It's like it's one way of generating entangled structures, but I'm not going to talk about it. I'm going to talk about a kind of qubit that doesn't have anything to do with spin. And I call these synthetic qubits. So I want to start with a shallow square well, something that just has a single bound state and then a continuum of free states. And so now, what I mean by a synthetic qubit is I'm going to have a pair of wells, and I got a scalar particle. And this scalar particle shares these two wells in some proportion. So there's only one bound state, so it's a little bit of one bound state and some more of another bound state. And it's a complex mix of the two. So really I can describe it by two complex numbers, a and b, and because it's normalized, the norm of a squared plus norm b squared equals 1. So very much just like a spinner, but no connection here to magnetism or rotational properties or anything like that. So I'm going to take a pair of these synthetic qubits. So I've got the first one in the orange box and the second one in the purple box. Now we're still in line land, so it's really, I just mean everything's happening on a line. And I've got 4 distinguished positions. I've got W, X, Y, and Z. The first qubit has its 2 wells at W and X. The next ones are at Y and Z. And the complex amplitudes at each of these locations are respectively A, B, C, and D. So I try to keep it simple by keeping everybody, the beginning and ending of the alphabet, and in order. So let's see. So now I'm going to go to this product picture, this picture of these. So I've got two particles, remember? I've got two scalar particles, and they're each in these pairs of wells. And now I'm going to look at it in 2D as a product function. And so I've got W and X on the lower axis and Y and Z on the upper axis. And the amplitudes, everybody has to live in one of those 4 green dots where they intersect at, WY, XY, WZ, XZ. And those are the amplitudes. AC, BC, AD, BD, because it's just a product function. I started off, I made it. Now, we talk about interactions being local. So what does this mean for a two-body system? So it means that we're talking about the interaction basically only happening when things are almost right on top of each other. So modeled by a delta function. However, when I go look at this picture again, whoops, it's right there. What this basically means is that dashed gray line is where the interaction is. So when I made these wells, they're not touching, but the locality, this potential, when I express it in this plane, is really a potential that exists on this diagonal. All right, so now let's start moving them together. So I'm going to take the purple ones and start moving it to the left towards the orange ones. So what does that look like? Okay, so you see the y coordinates are moving down. And I should have had I guess I'm stretching this little synthetic quibit because the z's ones are staying still, but it doesn't really affect the result here. So when I've moved that y part of it down far enough, move that left one down so that it's actually overlapping, it means that lower right quantum well is now approaching that diagonal where the potential is strong. So what happens? Since this was a barely bound system anyway, I've got amplitude in this well, and it's going to no longer be bound because it was barely bound, and then I shoved this interaction potential down the middle of it. Presumably it's strong enough in this case to actually drive all the amplitude out. So what happens? Well, the waves in that little well on the right start radiating out. Maybe some of them fall in these other wells, but they become free waves for the most part. And what I've got left is this. I've still got my amplitudes at WY, WZ, and XZ, but that one corner well is now empty. I've got free waves radiating off in space. All right. So now it's a little inconvenient to have those free waves. So what if I just surround the whole system with a bunch of measurement devices? So any free waves are going to pass through them and get detected. So either what happens, and this is the only place I use Copenhagen or any interpretation of the wave function here, is if I measure something, then I know that the particles got out. But if I don't measure anything, it means that all that's left, everything is left in those 3 wells. Now I'm going to move that well back out. So I'm going to move that purple synthetic qubic back to the right, and this is what I've got left. Now, whether you believe that I've sliced my system in some many worlds way, and this is the one I'm left with, or it collapsed, and this is what I'm left with, I now simply can renormalize all of these if I want. Renormalize this system. Not a really essential point, because if I don't renormalize when I take my measurements, I end up having to normalize anyway. So what happens here? So, well, this system is clearly not a product function. So if an orange particle is measured at x, then the purple one cannot be at y. It must be at z. So this is an example of how I've just used scalar particles to create qubits and create an entangled state. So at least it justifies that this kind of entanglement is possible. Now what about spin? So I can replace these continuous variables x1 and x2 with just discrete locations. And I could call them S1, S2. I could call them 1/2, -1/2, or up and down. And it looks very much like the previous picture. Of course, these locations don't correspond to anything positionally anymore. And not surprisingly, I can regroup these as I usually do with angular momentum. I can define new variables and take linear combinations of them, symmetric or asymmetric, depending on if they're fermions. And so my point is only to make you see the connection to the previous picture. And so we've got some product functions, up, up, down, down. The general function is a linear combination of all those cases, just as our original synthetic cubic pair was. But then there are also wave functions that aren't product functions at all. And those are the ones that we call entangled. Somebody once brought up to me like whether or not symmetry, the symmetry induced, like the anti-symmetry of fermions, means that creates a kind of entanglement. And it's not usually the way we think of it, but I thought it was an interesting question because they're not product functions anymore, but I guess they are anti-symmetrized products. So I think it's still interesting to ask, like, should I think of fermions in general as having correlation? Okay, so last question is, the last point I wanted to make was about this communication and correlation. So if we have the above wave function, when we have them move in opposite directions, like we split our packet and have it move in different directions, so there's a spatial component to it as well as a spin part, then when you get to one place, you measure it. If you measure it up there, then you must get them down at the other location. So it seems like something maybe has happened. Like maybe there's been some communication that happened very quickly, even though these measurements might have been very far apart. I guess it certainly doesn't allow us to communicate. It's sort of like I could give you a set of ones and zeros that says the Gettysburg Address, on one end, and I just get zeros and ones that says the Gettysburg Address on the other. But that's what it's going to be, is all determined based on how I've entangled it, at least insofar as that the one side will be up and the other side will be down, or 1 and 0. So we don't get to make the decision at the end, even though we know what the other person's gotten. Now, the final thing I wanted to bring up here is this geometric picture somehow useful to make progress on some of these other problems that we have? Like, could we use it to explain measurement? In other words, if we could very carefully describe macroscopic matter using many-body wave functions, would we get a kind of splitting of the universe into different branches that seems to agree with our probability statistics? So in a sense, the universe really does split. but of course this would be require being careful. It would be require us to be much more careful than just simply throwing out block wave functions. The kind of wave functions we use in solid state physics are a little naive when it comes to this point. They still have tremendous amount of information in terms of transmission properties and conductivity and thermal transport. But I would say that you've got to be more careful than that if you actually want to describe a true classical macroscopic body with a wave function. And then, to me, the biggest mystery in terms of quantum mechanics is thermodynamics. Many of us have learned the partition functions, quantum partition functions, density matrices, and that whole approach. But nobody's ever really explained why these things come about. There's been some recent work by people like Popescu and Goldstein, which I don't find compelling myself at all. I feel like it's more math that's still not getting to the core of what's happening, of how does thermalization occur for quantum mechanics, because quantum mechanics gives us linear evolution. Technically, nothing should ever change. So there are various hypotheses which seem a bit ad hoc to try to make this happen. But the sad thing is that most people don't even realize this is a big open problem. I mean, if you read books from 50 years ago, even Landau's book in the introduction, it's clear that this is a big problem. I feel like nowadays, if you read a book on statistical mechanics, it's often hardly even mentioned. Many people who even do research in this don't seem to understand what a big conceptual hole we have with regard to statistical mechanics and quantum mechanics. Even though some of our calculations work well, but there's a bunch of things that we can't do as well. So I think that's a good place to end my talk and suggest what I might talk about later.